And hello, good morning, good afternoon, good evening, and welcome to session 2 of Logic Application and Designs for the Automotive and Industrial Marketplace. Our presentation team today, again, we have a new member joining us today, Javed Ahmed, who will be speaking to us later on specifically about some of our new future products. Also joining me today is Christian Backhaus, who will be working on some applications. My name is Tom Wolf, and I will be your host for today's session. Again, thank you very much for attending this session. We believe that many of you who are from the first session who joined us for the second one. If not, just a couple of points for those of you that might be new to this group. All of the materials which are presenting for both this session as well as session 1 are available. You will get a link after this session so that you can download those as well as listen to the recording again at your convenience. And also wanted to make a note on why we've combined automotive and industrial together. We're looking at both product markets in this case, because we're seeing this continual move of the industrial marketplace into high reliability, which turns them into automotive applications. So the products that we will be talking today are both automotive, but they are of great interest to the industrial and even the high-end consumer market, including medical applications. So please look at it from that point of view. And we encourage you to please send us questions. You'll notice in the sidebar of your pop-up screen, you can type in questions at any time. We're reserving time at the end of this presentation to address those. For those of you that were on session 1 and we were unable to answer your questions, we've reserved time, we've captured all those questions, and we will try to answer those as well for today. However, all questions and answers will be provided by a link after the presentation for you to review at your convenience. So our agenda for today, in session 1, we looked at a lot of our product information, some very specific application informations on some of our transceivers, some of our shift registers, some of a variety of devices. Today, however, we're actually going to jump back in time to look where logic came from. Now, this isn't just for interesting trivia. It's important to know what logic has gone through its many years to understand what it is doing today and what new products will be coming in the future from logic as well, too. We'll look at the overview of the Nexperia Logic devices. Again, we saw some of that in session 1, but we really want to look at how do you focus from so many products that we build for the specific devices you need for application. So we'll be looking at selection and how to determine one part, one family over another in those groups. And then we will look, after we've looked at the past for long enough, we will then move on and look at the future. What is the roadmap from Nexperia products, and what are the trends in new logic devices that will be coming up? And then finally, one of my personal projects that I'm involved in will be a preview of the Logic Application Handbook, which will be released after this presentation itself. And then again, we will hold time for the Q&As. So let's start back at the beginning on this. And again, it's not for trivia, it's to understand why logic parts are the way that they are today. All of you know or should know that the transistor was invented around 1950, the semiconductor transistor. Integrated circuits were invented at the end of the 1950s by Jack Kilby and Bob Noyce, who determined how to put multiple transistors onto one piece of silicon. However, at the end of the 1950s, the microprocessor as we know it today was not invented till the 1970s. So computers obviously were built between the end of the 50s and the beginning of the 1970s. How did you do it? And that is where the story of logic begins. In particular, it starts in the Apollo guidance computers, which were built in the 1960s. There's a photo of it in the upper right-hand corner there. And by all indications, it was a pretty powerful computer. Look at the specifications. It was a 1 megahertz of ALU clock speed on board. It had 1K of RAM and 12K of ROM on board. Now, that doesn't sound like much today, but remember, even like the original personal computers in the early 1980s were only in the 4 megahertz range and were not that much more memory. So literally, this machine was the dominant power up until the 1980s. So it was way, way ahead of its time. Now, this unit on the right, each one of those in 1962 cost $200,000. That's in 1962 dollars. And just that for inflation, each one of those was $1.5 million. About 75 of them were built. Now, the reason I'm going to claim that logic was king in the 1960s is because half of the price of that unit, $100,000 in 1962, was the cost of the logic devices. In particular, because there was no microprocessor or anything in it, every single function on board was built with logic devices. In particular, they were built with 5,000 pieces of the Fairchild MicroLogic Type G RTL 3 input NOR gates. The same device was used completely through it. Each one of those cost about $20 each. $20 in 1962 dollars, that's $160, $170 adjusted for inflation today. So I think we can confidently say that logic was king. Literally half the cost of the computer was in the logic chips which were built on board. By the way, if you're more interested in this, there's a wonderful series on YouTube which gets into the Apollo guidance computer. One has recently been discovered and is being restored, and you can watch all the restoration and see these devices as they're built. So that's 1960. That is the beginning of logic, where literally if you wanted to build a computer, you built it out of discrete logic devices, built the ALU, the memory, the shift registers, everything was built with discrete standalone logic devices. Now let's jump up about 20 years. Logic in the 1980s, everything then was the SBC, the single board computer. And here's one of the common ones. This was an 8080 based S100 CPU card. And don't worry about exactly what it did, but if you look at it, you can already see the trend. In the center here, this large 40-pin device, that's the CPU. The microprocessor, which is now the heart of all single board computers and ultimately all computers after that. All the devices around it, though, are either 82XX family devices, which were essentially complicated logic supports for the microprocessor, or just plain logic devices, a lot of LS244 buffers, 373 latches, devices like that. So you can already see the trend of what's happening. The microprocessor has taken the heart of the computer, and logic is beginning to move out towards the edges, doing I/O, peripherals, and timings and things like this. So like I said, this was the S100 card in particular. There were many others that were built at the same time. There was the multi-bus cards that Intel had and a number of others as well too. But the concept is the same for them. Microprocessors, logic is beginning to move to a support function for it. Let's jump up another 20 plus years in particular, which is really the state that we're at now. This happens to be a MacBook Air motherboard, but if you look at the motherboard of any modern computer, you're going to see essentially the same thing, is that the board has been shrunk down so much is that now I've got typically a main microprocessor, an applications processor, or a front side bridge, depending on what the architecture is, a whole bunch of memory on it, and then I've got a lot of other devices on there. Believe it or not, buried on that board, including the MacBook Air, and again, virtually every computer that's made, are logic devices. Yes, they're so small that you can hardly even see them in the resolution of this picture, but the functions that logic did in the 1960s, the final stage of buffering, the final stage of latching, the final stage of switching analog signals in and reset in, continues to be done with discrete logic because that is the best way of doing it. Logic devices have a higher tolerance because they're built on bigger geometries, so they have the ability to drive more current than the SoC or the microprocessor, or tolerate higher voltages or high ESD. So you can kind of see the trend pretty obviously there. In summary then, logic over the last 60 years has moved from being the core, the entire computer, everything about it, into the peripheral functions. It's moved from being a computational device. You used to be able to buy 4-bit and 8-bit ALU logic devices that you put data in and it would add them or multiply or do mathematical functions on them. Not so much anymore now. Now you've got logic devices doing I/O defense. Or another way to look at it is that logic has gone from those gigantic parts, those 82XX we saw in the S100, down to very small single and dual gate devices. The concept is just the amount of logic, just where you need it, not gigantic parts on it. So it's still there. To use the American football analogy, that logic is really no longer the quarterback. It's now the defensive line between what you can consider the delicate microprocessor, meaning small voltages, high frequencies, low ESD protection, connection between that device and the outside world where we still have ESD and high voltage and high drive current and LEDs and all the things we need. So logic has changed over the years, and that's really the story of what we want to talk about, is because it continues to innovate and continues to change every year from now on. So with that, I'm going to jump to an overview of the Nexperia Logic devices. Now, we did this in session 1, so I don't need to go into as much detail, but it's important to understand the products that Nexperia and most logic suppliers build to see what functions are available and, again, where those innovations can occur. Now, this is the way that Nexperia categorizes what we call logic. Everybody defines it a little different, what part is or is not logic. But these are the 4 main groups that Nexperia uses, and if you go to our website, you'll see that we even use the same color scheme for it. Starting in the upper left, you've got the asynchronous interface logic devices. Asynchronous meaning there's no clock. It does something to the data when the data gets to it, but there's no predetermined time when that would happen. Technically, a lot of the logic gates are doing that, but things like buffers and transceivers and Schmidt triggers that are used in the outside world to filter out analog signals and turn them into better digital signals, those are all asynchronous devices. By comparison, on the lower left, you've got these synchronous interface devices. These devices all run on a clock. There's an input clock or a latch enable into them so that everything is synchronized. As speeds of computers get faster and faster, you really don't want a lot of asynchronous things happening. You end up with all sorts of time delays in it. So things become more and more synchronized. So there's a whole family of parts in the logic family which are built for synchronizing or resynchronizing signals between the microprocessor and the memory or an external bus, things like flip-flops and latches and FIFOs and shift registers and devices like that. Again, these are still very popular in the higher performance logic applications. In the upper right is actually the biggest growing area based on that history trend that we just saw, this idea of I/O expansion. A pin on a microprocessor is pretty expensive because there's already a lot of pins on them. I mean, modern processors have thousands of pins on them. To add a pin there is relatively expensive. It is better from a efficiency as well as sometimes just from a simple routing, board routing application to put your I/O on an expansion port outside. Use 2 pins to shift serial data out to an external logic device and then have it shift data out on an 8-bit port, a serial in parallel output shift register, for example. It's more cost effective to have those pins on the external device in the logic device connected to the external devices it's driving than to connect them directly to the microprocessor. So there's a lot of growth in that particular market as well too. And then finally, in the lower right-hand corner is the original control logic. These are those parts that made that Apollo guidance computer possible in the first place. It is the gates and the comparisons and the parity generators, those things which are doing the true Boolean functions, ands, ors, nots, and inverts. And they're still very, very popular and out there. So this is the look at the, the current state of the analog and logic portfolio marketplace. How do you stay relevant in logic, though, for 60 years if logic by its basic definition really hasn't changed? Well, you have to continually innovate. So starting up here in the upper right corner, because this truly is a circle of time, you know, you have to look at, we develop a new product and then based on that, continue to promote it into the marketplace, get customer feedback, and then modify it again. So starting in the upper right-hand corner, one of the biggest innovations in logic is changing the packages for those. Everybody wants something smaller. You saw the MacBook Air picture. You can't even see the logic devices in it because they've shrunk literally to the point where they are smaller than the head of a pin. And that's what that photo is. That's actually a photograph of the GX package, the 5-pin diamond pack, sitting on the head of a sewing pin. It's only 0.8 millimeters across on a 2-millimeter head. But that is required. These are the same functions which were available 50 plus years ago. They've just been shrunk down to fit in a smaller package, a single gate, a single OR gate, a single AND. Other functions designed specifically for the automotive marketplace was the side wettable flank device. It's nice to have a leadless package, but how do you determine once it's soldered down that these soldered joints are good? You can't see the leads anymore. The pads are underneath. So you either had to X-ray the device, which is an extra cost and an extra assembly stage, or Nexperia helped develop the package which brings the plating up the side. So when you solder this part down, the solder wicks out around the edges and you can see the fillet on the outside to know that the part has physically been soldered. You can visually inspect a part where you can't see the pads to know that it is indeed soldered correctly. The other one too is the CSP package. We still get requests for die business. Can you sell us the die so we can mount it in the absolute smallest package? There's a number of reliability and quality issues involved in doing that because it's bare die, which has only been tested in an early stage. Instead, we have CSP packaging, which is a chip scale package. It's essentially the die with solder bumps on the back of the die itself. It's not even encapsulated, which gives you virtually the same size as direct die placement, but it gives you the quality of being a real package that we can test before it goes out the assembly line. So it gives you the best benefits of both of those. So those are some of the package things which have occurred. Other things which have occurred too is that the family of logic continues to grow. You know, all of the part numbers in logic are defined. The 7400 is a standard part number. the 00 always means the same thing. It's a NAND gate, whatever logic family you're looking at. Well, we continue to add new parts to that family, primarily by combining functions together that were never available before. For example, if you need one AND gate and one OR gate on your circuit, that meant 2 packages. However, why can't we combine them? So we have a whole family of parts where the single package has one AND gate and one OR gate on it, or 2 buffers and 1 inverter, or an inverter and an OR gate. The wide variety of combinations to help you reduce the size of your design by combining these parts together into smaller packages. So it's kind of a packaging logic trick, so to say, that defines new part numbers. Other things are like configurable logic devices, a device which can take on the properties of a different logic function depending on how you wire it. You don't program it, but if you hook the pins up one way on it, it acts like an OR gate. You hook up other pins on it or ground certain pins, and it acts like an AND gate or an exclusive or a buffer. So you can buy one device, use it on multiple places on your board, and each place on the board, it has a different personality. That's the way that you innovate logic, by continuing to change its functionality. Other things are, in the lower left, is you need to change the family type, the process. The process family follows the microprocessor. Back in the 1960s, which were actually RTL level devices running at 15 volts or higher, the logic families needed to be 15 volts. Microprocessors, when they were 5 volts, needed a 5-volt logic family to support them. Then 3.3 and 2.1 and 1.2 and 1.0. Every time the voltage node for the microprocessor drops, there needs to be a corresponding logic family. The newest family is our AXP family, which can operate down to the 0.8 volt node, which the newest microprocessors are using. So again, the process family is continually tracking that to allow you to connect your newest microprocessors to the rest of your digital system. Other things are integrated solutions. For example, there's a picture of the LED sign here, very popular. Everybody designs it essentially the same way. Your microprocessor at 1 voltage talks to a shift register, which talks to power MOSFETs, which drives the LEDs directly. Because everybody did it the same way, we developed a single part, which essentially integrates all those together. The translator plus the shift register plus higher output drive, because that's the way everybody did it. And then finally up here in the green is sort of, because we've been in the history business of logic for so long, we've seen competitors come and go in other families. And at certain points, it makes sense for us to enter markets that other people have abandoned. Things like the LVA family or the CB3Q, where those are families which were invented a long time ago. Maybe we didn't have them, but as part of our portfolio, we're adding them. So not only are we inventing new products, new innovations, but in some cases, we're filling in with older technologies that give you one portfolio to answer pretty much all your logic needs. So a lot of history, a lot of information on the parts in particular. Let's get down to the application. Of all these part numbers, how do you pick the right device for what you're looking for? So here's the timeline again of where the stuff came from. Nexperia is a descendant of NXP, which is a descendant of Philips, which was part of Signetics. Signetics was the beginning. So we've been in the logic family, the logic business, since the 1960s, 1970s timeframe. In fact, some of our devices are still available today. The HEF family, for example, which was developed in that time frame, you can still buy today. It has a very long history on it. And here's some of those other things that happened. Like I said, 1970s, there's the HEF family, also known as the CD4000. Those parts are still in production today after nearly 50 years. The HC and the HCT family, 74HC00, those devices were built in the 1980s and are still the most popular 5-volt logic family. So they're still available as well too. The LVC joined in the 1990s, the AUP and the AXP family. Again, each new generation arrives because the processor and the support logic around it, the support devices around it, need a new voltage node, and that's what creates them. Now, this is the eye chart of the presentation. We saw this in part 1, and it shows the 20 different logic families that Nexperia currently provides. So it gives you all of these different devices in an interesting chart form. But if you're looking for a logic solution, how do you find it? So what I've done now is I've prepared some graphs which show this information graphically, depending on how somebody would typically select a logic device. The first way might be by performance. What's the speed of your CPU? What are your clocks? What is the highest performance device, the highest performance logic family that you can get? The faster devices are at the bottom, the slower devices at the top. So that same chart you just saw is now being seen pictorially, and you can see that the CBT and the CBT-LV logic devices, which are really switches, they are the first devices on this family that are available. They are the fastest ones available. And then in order of slowing performance, I go up through the dark green here, the dark blue are the low voltage families, the green are the high voltage, 5 volts and above families, all the way up to, there's that HEF, that metal gate part, which is, logarithmically much lower in performance, but it's a nice high voltage. If you want to run at 12 to 15 volts, that is the family to select. So when you're looking for a part, this is a good way to start it. And by the way, any of you that are about ready to send in a comment that these bars should not be horizontal, absolutely agree with you. They actually should all slope down to the left, because as voltage decreases, the performance decreases of these devices, considering these the optimal performance values of the parts. It just doesn't chart well if you try to draw it all in the same part with all sloping curves on it. But again, use these as a relative guide to determine which family you need if you're selecting your logic based on performance parameters. Now, another way you might select logic is by its power consumption. How much static power does it draw? For battery-powered applications or anything which is electrically or thermally sensitive, how do you lower the consumption on it? So here we have, again, ranked from the bottom to the top with the less current, the most power efficient, up to the most, I'll say, power hungry logic devices, all in order across their operating voltages. The AXP, which is one of those new families we developed, is the best in terms of its power efficiency. Lowest voltage, lowest static current consumption, up through all of the low voltage families, the high voltage families, and then into the legacy, the HEF, and the fast logic as well too. So again, if you're looking at something and it's power critical, here's a chart or a way of selecting that right device. And then the next one is by the output drive, ranked in order of how much power you can drive so that you can hook a LED directly to the output of the device, for example, is that you could put, from a high voltage family, they rank from the HEF family, which is the lowest current parts, all the way up to the NPIC family, which is a specialized LED shift register device, which is 100 milliamps per output on it. So again, if you're trying to drive something directly, take a look at these parts to determine which part will give you the output current you need. And the same for the low voltage family. The AUP is let's call it the weakest of the family in terms of its lowest output drive. Of course, it consumes low current in the process as well too. If you want to drive LEDs or devices directly off of a low voltage device, take a look at the LVT or the ALVT family, because they can source 32 milliamps or sink 64 milliamps, which allows you quite a bit of IO drive directly off of the logic device itself. And then one more ranking as well too. This is specifically about the packaging. Sometimes your system may be ranked specifically on its package size. You're putting it into a credit card or something very thin. You have a minimum height. So in declining height, these are the highest on the left, the tallest, all the way down to the lowest, the shortest device on the other side. Please note, however, that as you tend to get lower, the pin pitch drops at the same time. So this is decreasing pin pitch as we go across to the right. A smaller, lower height package tends to have smaller pitch devices on them, which may require some special soldering and special handling. But again, if you're looking for a logic solution, not much height for it, here's a good way of looking at the technologies which are available to support even those applications. And then finally, logic package by lifetime. Actually, one of our questions on lifetime, we'll deal with that later. But all packages have a predictable lifetime. They start out as a brand new technology, a brand new package with very few vendors building them. So they may have a cost premium on them because they're not in mass production yet. At some point in time, the parts begin to ramp up and you begin to see more and more vendors come in. When you get into the maturity phase, all logic packages go through a phase where there's many suppliers building them. The supply is great. Even if the demand is high, the costs are as good as they're going to get at that particular time. And then at some point in time, manufacturers begin to stop building parts. They begin to end of life certain package types. And at that point, that is where the cost will start going up. And you need to be aware of that issue as well too. So if you're looking at a package for an automotive application or for a long-term industrial application, keep in mind that all parts have a lifetime. Pick parts that are on the rising edge or in the mature stage because those have the longest lifetime available for them. Packages like the TSOP, the SSOP, and the lovable dip package, those are pretty much near their end of life, and you just won't find many suppliers or many options available in those particular packages. Okay, so with that, we've kind of seen the history of logic. and where we've been in the past. What I'd like to do now is pass the presentation over to Javed, who will tell us where Logic is going in the future.
Hello, everyone. Thanks, Tom. I think I have a new respect for Logic devices, being center in the place for putting the first man in the moon. Folks, hello, good morning to everyone, good afternoon, those joining from Europe. My presentation is going to be mainly on the new products that we are working on and plan to sample and release in the next 6 to 9 months. So with that, before we start get into the specific new products, I would like to kind of go over the 3 different product families that we have within Nexperia's Analog and Logic business group. So as Tom mentioned, Logic devices include both the standard Logic and the I/O expansion and interface devices. Tom covered the standard Logic in pretty detail. I'm going to be mainly talking about new products in the analog and interface IC category. And as you can see there, we added a new category there, which is a power management IC that today we don't have any product to announce, but we are actively working on bringing out new product that will be announced sometime in the middle of next year. So please look out for those announcements. All right, so as also was mentioned in the earlier presentation, the translators, there's a lot of activity going on there, and this is mainly driven by the need of the lower process node devices, the microcontrollers, the memories, and the processors going to lower voltage nodes, and they have to still be connected to the rest of the world ICs, that's the legacy ICs, the analog ICs, and they are staying with a higher voltage node. So the translators act as a good in-between device to connect the two. As shown here, we have the LSF, NXS, and NXB family of bidirectional translators. And by bidirectional, it means it can communicate in both directions, as shown here, between master and slave, for example. In this case, for an I2C interface. And this particular family does not need a direction pin, so that's why they're called AutoSense. So they can automatically translate on either direction on its own. So the LSF family, the NXS family, and NXB family, the key differences between the 3, some of the key features are shown there. Here in the slide, I'm not going to go through each one of these, but you can see the voltage range, the supply range that you can translate between from one domain to the other, the speed, and then also the target application that they're used in. And as I was saying, one of the key difference here is the amount of capacitance that these translators can drive in terms of the load capacitance or the straight capacitance of the trace. So the NXS and NXB are active translation, and LSF is a passive translator. What that means is that in active translation, we do have a one-shot accelerator, which basically turns on these 2 transistors at the right edges from low to high and shorts out the pull-up resistor, thereby improving the rise time. So you can have better signal performance over the connection from one side to the other. The devices that we are offering are in 1, 2, and 4, and 8 channels. And for the NXB, we not only have active acceleration on the low to high, but also from the high to low. So if you had a long trace length and you had more straight capacitance on the line, then NXB would be the one to use. But either of the 3 families can be used for bidirectional AutoSense translating. Okay, the next one is in the I/O expansion. We have a full portfolio of analog switches in the 74 family and bus switches already available. Going forward, we are focusing on switches with more differentiated feature, higher performance feature, like in this case, low R-on, low leakage, low power consumption analog switches, and switches that are specifically tied to a given application. So as you can see here, we have different configuration for this low ohmic analog switch, and these are in development. They'll be offered in a TSSOP 16 package, and this is an example of the application where, in this case, you could have a bank of reference voltages that needs to be measured and the LDOs calibrated. You could have a bank of sensors all connected with low R-on, with low delta R-on variation between each of the outputs, and they're connected to an ADC via an op-amp. So overall, this switch delivers the need whereby it saves on the cable cost, the cabling, and also enables seamless monitoring of multiple resources in the system. The next product that we have also in the switch family is the low switching induced transient SPDT. SPDT stands for single pole double throw switch, and it's shown here. We have two parts in this class, and that's shown listed here. One is for the negative voltage swing, and the other one is for the positive. Sample date shown and release to market date shown here. And these switches are designed for specific application, and the application is shown here: the active antenna unit, home medical devices, point of sale equipment, and so on. And I'm going to just show an example here of an active antenna unit which uses such a low transient switching transients switch. So as you know that 5G antennas have an array of antennas. It's not one antenna only, and each of these antennas are powered by its own power amplifier and RF unit. And the switches are kind of used here to power the power amplifier. So in a normal case, when the system comes up and the DAC voltage goes to its desired value, then the switch is turned on, and the power amplifier turns on from the power coming out from the DAC. At that point, there's a real need for a low overshoot, so that's why these switches meet that requirement. And also, in case that you could have an antenna with, let's say, 8x8 or 64 active antenna with 64 individual antennas, and if one of the signal path for the antenna is faulty and needs to be taken out, then this switch can be disabled, whereby it disconnects the supply for the power amplifier to ground, and so safely takes out that path from operation. So the rest of the system can still be running, and can at a later point be replaced because most of these active antenna units are installed in a tower or some high structure. Okay. The next device that we are also going to be sampling next year is level translating I2C edge accelerator, as shown here. There are three main functions for the device. So if you just look at this device, this example is for an I2C, is that it provides signal regeneration, signal acceleration, and of course voltage translation, all built in. One of the key performance features of the device is it has an edge acceleration, and it is active edge acceleration, whereby there's current induced, and it improves the rise and the fall time of the signal. So again, if you look at higher speed I2C bus, where you have like 1 megahertz kind of a signaling going on, you have a long trace, a long capacitance, then you will find the low pass effect on that line, whereby the edges would start flattening out and will close the eye at the other end of the line. And what this device does, it improves the rise and the fall time, so thereby you have a more open eye and you can drive a longer trace distance. So in summary, this slide here shows the timeline for the devices that I just discussed in the previous slides. And so you can see the translators here, the interface devices here, the analog switches here. The ones that I did not cover is specific translators for SIM card and SD card. These are also being developed for the cell phone market. And the triangles, the red triangles here, show the engineering samples. So you can get engineering samples, you can get a data sheet for the part, and demo boards in some cases. And release to market is shown in the green triangle here. So this is just for your reference. Watch out for updates on these. But if you have any interest on any of these devices that I mentioned, including the analog switches here, feel free to reach out to your local sales contact in your region. Also here shown is a family of logic devices in different package formats. So in this case, it is DHX QFN, which is the industry's smallest footprint, and it's with a 0.4 millimeter pad pitch. So in summary, as Tom mentioned, logic products have been around for more than a lot of you in the call, and they'll continue to evolve and thrive. There'll be need for these devices. Of course, they're not in the forefront of technology as technology is moving, but they are definitely needed, and we are very much in the center of it. We are here for the long play versus some of the competitors who have come and gone. But Nexperia will be very much here to serve your needs. So going forward, as we see, translators will have need for higher speed, higher frequency support, wider voltage range, as we are seeing with lower voltage nodes of the microcontroller and microprocessors and the digital devices. Even there's a talk about 0.6 volt logic in consideration, and also need for AutoSense automatic direction control because less number of pins are needed for translating or available for translating. And then the analog switch, as the saying goes, sorry, this is my timer. As the saying goes, as you have higher speed, a square wave will look like a sinusoid, and so on. So, these are some of the things in the areas that we are working on to meet the requirements. And finally, on the packaging technology, like again Tom mentioned, we have smaller footprint, and we are going to a smaller footprint without necessarily going to a smaller pad pitch, because there's a limitation on how low we can offer in pad pitch. With that, I'm going to hand over my presentation, hand over the presentation to Christian. Christian.
Thank you. And also from my side, good morning, good afternoon, and good evening to the audience. I would like to introduce briefly the Logic Handbook, the Logic Application Handbook that we have now almost released, is in the final stage now. We have in Nexperia already for quite some time the Power MOSFET Application Handbook, and 1.5 or 2 years ago we have also released the ESD Application Handbook, and now as a third application handbook here from our company, we have created the Logic Application Handbook, and the scope is here to enable our customers and the engineers in the customer companies to understand and use and also design in the logic products that Nexperia offers. So it's mainly dedicated for engineers, and should be nice to read. We do not mention all the product portfolio and that we have in the selection guide. So this is no second selection guide. This is simply generically explaining how to use our devices in various aspects. So the target users are here engineers in the customer companies who are dealing with our products every day and have to need to use them and want to know various aspects about it. So the storyline here, logic devices and their usage is pretty generic. We can use we can find our logic devices and all kinds of logic devices. So therefore, we do not really cover here all kinds of applications that we can use our products in, but we want to address all the requirements that people who are using our devices are confronted with. And that is leading to the following storylines. We give a brief introduction, and then we cover the basics about the logic devices and things like binary code and logic equations, truth tables, and simple logic functionalities here in our portfolio. And a second part of the second chapter is the data sheet. The data sheet is containing all the properties, but very often people are asking us how to use the device under these and those conditions. And here we explain many properties and behavioral aspects of the devices which are not covered fully in the data sheet, but are useful for users to understand. And The next chapter here is the power considerations. Power is another important aspect when using our products. You need to understand how much power is dissipated by the device and under which conditions. So therefore, we address here static and dynamic power calculations and influences of aspects like duty cycles and slow inputs. These are also dependent on various process technologies. Therefore, we also address that in, for example, a table like this here. And we explain how to calculate the power dissipation capacitance and how to use it, and give some recommendations for calculations for power dissipations. And this is mainly done for both CMOS and also for the few bi-CMOS products that we still have in our portfolio. The next important aspect is the timing. For timing, we cover the synchronous and asynchronous logic devices here, and very important here are things like setup and hold times and propagation delays that we explain, and these are mainly valid for flip-flops and latches. And apart from the timing properties of our devices and the general requirements for this, we also cover general timing aspects like skew and meter stability, and also recommend what can be done to mitigate meter stability in this case. And these little figures here are examples that I have pasted in from the Logic handbook that I use to illustrate our explanations for the various timing aspects. Following the timing, we are explaining the interfacing aspects. Interfacing has also lots of different sub-aspects like level shifting. There we explain what level shifting we offer and what mechanisms are used for doing level shifting, like, let's say, simple clamping diodes or over voltage tolerant inputs, and also single and dual voltage sources. And then apart from the mechanisms for level shifting, we also look at various features that our devices are offering, which are also interface aspects like Schmidt trigger inputs, the eye-off feature, and also, like illustrated here in the in the example in the picture, the bus hold feature, which is useful for when inputs are getting disconnected temporarily. And then we also, again, look at general effects associated with the interface, like ground bounds and VCC bounds, and also look at some recommendations how to avoid ground and VCC bounds. In the next chapter, we look a bit into our portfolio a bit deeper, and the various segments. The segments have already been introduced by Tom in his presentation earlier. And here we look at all these product portfolio devices generally, and explain how they behave and what the differences are, for example, between analogs and bus switches. And then we cover these asynchronous logic like transceivers, translators, buffers, and inverters, and also the synchronous logic. And we explain partly also how to use certain devices in an application environment. Here in the picture, we see the example for the AutoSense translation. That is a little bit more sophisticated. Javed has just addressed them in his portfolio and roadmap overview, and here in the handbook we explain what must be done in order to use them in an application, and what is important to configure the pull-up resistors and to select the voltages and so on. So this is a device which needs a bit more explanation, and then this is here given in the Logic handbook as it would be, for example, in an application note. The next chapter is the package chapter. Nexperia Logic has a wide portfolio of packages, and here we explain the internals of our standard packages and our mini logic packages. And of course, for application, it's also important to understand what we need to address for soldering. Here we have things like reflow temperature profiles, and we explain also the thermal resistances here in this model, for example, and how we characterize our thermal our thermal resistance. So for the package chapter, it is really a lot of content in there, which is helpful to understand which package should be chosen, either leadless or leaded packages. And there's plenty of, let's say, inside information given, which is interesting and useful for the application engineer. Then there's also a brief chapter about our automotive quality. There we address what is AEC Q100 qualification and what we are doing to assure qualification and to assure reliability, what monitoring is done, and then some other automotive quality aspects like Six Sigma design and zero defect tests are explained and also covered here in this chapter. Then in the logic family chapter, we cover the most important and most popular process families like LVT, ALVT, AVC, and until AXP. And there we explain internal aspects like how are the IOs constructed, and very important and very useful also, and covering many questions from support is that we have illustrated all input and output behavior curves here. We can see here the ICC over VIN for a Schmidt trigger input, for example, and that is a very open subject of support questions when people would like to know how the curves behave and what current is being drawn in at which voltage, and therefore these IO curves also with regard here or with respect to temperature can be very useful to understand and to estimate current and power consumptions at various temperatures and other conditions. So, sorry. Some special features that every logic family has are also explained and mentioned here. And the next chapter is the FAQ, the frequently asked questions. Generally, I can say that the complete storyline of this logic handbook is also the consequence of condensed experience with customer support questions. So that's very much oriented to that, and specifically this frequently asked question chapter is dealing with the 25 most popular questions that we have selected, and of course we're also giving the answers here, and that should be very helpful when using our devices. And if there are questions, then it is quite likely that one or the other question can be already found here in this chapter. And then we have also some useful appendices, like the list of logic functions here. There you can see that in every logic device name, the name is indicating the functionality, and this table here answers what function is assigned to which number. So that is a very handy overview here with quite a lot of functions that we have in our portfolio. And then we also cover the package suffixes, not only from our company, but also from competitors. And then we give also, of course, the normal abbreviations and index list. The release of PDF edition is scheduled for October. That means this month. So we are waiting now for the ISBN number, and then we can release the PDF apart from some small fine-tuning modifications. It is ready, and then we will have the printed edition probably in early January 2021. So I'm looking really forward to send this out here to the customer so that we can then have a look at the logic handbook. Yes, and then we proceed with the question and answer session.
And thank you, Christian. Thank you, Javed. This brings us, like I said, to the question and answer session for our presentation today. Christian, could you flip one more page then, please? And these are the questions, apologizing in advance, that we did not get to in session one. And what I'd like to do is actually jump to the very bottom, to the second to the bottom question here, because the same guest has asked the same question again. So I thank you for your patience for waiting a week for the final answer for it. And that question was, does your Logic product exist in grade 0 automotive? For those of you that are not familiar with it, most grade 0 automotive applications are -40 to +150 degrees C operating. Most Nexperia Logic devices are grade 1, -40 to +125. We have a maximum junction temperature 150 degrees C, so operating at an ambient at 150 C could be difficult. Christian, are you aware of any testing or anything we could do to achieve a 150 degree operating temperature?
No, I'm not directly aware of what we can do now for 150 degree, but I can imagine that with the new packages, it would be rather possible, because newer packages are all implemented in copper, and very much limiting effect of former packages was the gold contacts. And I think that with the future, let's say, move towards more copper technology, move to 150 degree should also be easier possible.
Okay, so to the guests that asked that, then please contact your local sales or application engineer. This is something we'd like to investigate further. It may be your actual environmental temperatures, you know, how much thermal gradient can we take across the part, but it's something we definitely like to look into further. The second question that we received live for this for the second session today was, how can I get a hold of the Logic Application Handbook? And Christian, I think you addressed that. Is that PDFs we expect to post this month?
Yes, the PDF is actually done. We are in a final review session and do minor corrections here and there. And then it is important for us to get this ISBN number, and if we have that, then we can release the PDF, and that will be done as scheduled for this month, and I'm pretty confident that we will achieve this. So at the end of this month, the PDF will be available and can be downloaded from our internet site then.
Excellent, thank you. So please keep sending in questions if you have any for this session. What we're going to do is go back and answer these questions which we received from session one, and due to a lack of time, we weren't able to address. So starting literally at the top here. Does the dual source strategy mean that Nexperia can deliver all Logic devices at different plants, i.e. when one factory has an issue? Javed, I might let you answer this one, but I believe that our strategy is that we have the design capability to build products in multiple facilities, but are we actually building them in multiple facilities? Would you like to address that one?
Yeah, on selected products with high volume application customers, we do have plans that we start at the beginning of that project, and we have the capability of multi-sourcing either the assembly or the fab for that product. But that's more of a case-by-case basis, and we apply that. But across the board, we are a global organization with manufacturing and fab across the globe. So we can switch sites if we have the time and we plan for it.
Excellent, thank you. Our second question, do you have IBIS under VHDL AMS models for all of your Logic parts? Christian, I know you're working with IBIS. Would you like to answer that one?
Yeah, we have IBIS models for most of our parts. VHDL AMS not. We are having a plan to also provide, let's say, further improved IBIS models, because sometimes we experience that customers have difficulties with certain kinds of IBIS models, such as analog switches, for example. Nevertheless, we do generally provide IBIS models for all products. There's also an ongoing activity to work on future SPICE models for Logic parts, but that will take some more time.
Okay, thank you. And by the way, most of the IBIS models that exist are readily available on our website. Just when you go to the part, look under documentation, and if the IBIS model exists, which it usually does, you can download it directly. If not, again, contact your local sales or applications, and we'll find out how we can get that to you. Our next question, for functional safety, ISO 26262, are device failure modes and fit rates available? Yes, most of our parts on our public website list the fit rates, so that's publicly available. You can download it as you need it. We have FMEA documents by logic family that I've seen, so certainly at HC we can tell you the common failure modes of that particular device. Christian, any other thoughts on that?
No other thoughts.
Okay, good. So if you need that information, like I said, by all means, again, look on the website for it, or you can contact us as well too. The next one, what die functions are available in the high and low voltage device families? Goodness, most of them, I think, is the right answer. The product selection guide lists all of those, and there's also parametric search engines on our website. So if you're looking for a 740006, whatever the number is, it will tell you readily if that part is available for it. The answer is that it's a very comprehensive set. So all the devices, pretty much all the functions are available in most of the families. It's several thousand part numbers, as I recall, totally. So quite a wide listing there. If you can't find one, again, please contact us about it. Next one, do you have protocol converters, let's say from SPI to I2C? Javed, you kind of touched on that. Would you like to address that one?
Yes, sure. So we do not have today, and that doesn't mean we will not look into it, but at the moment we do not have any bridge device or protocol converters that we offer in the market.
Okay.
And we've also never heard of that request before. So that's the first time I see that request for SPI to I2C. Would be interesting to learn about what the application context here is.
Yes, and as we've shown, we enjoy innovating new products based on new customer requirements. If that's a new trend, we would definitely like to talk to you about it. So again, contact your local apps engineer. We'll look into that. The next one, can Nexperia support automotive lifetime of 15 years? I believe we touched on in the first session is the Nexperia guarantees a longevity for virtually all of our parts, not all of them, but most of them for 10 years. We publish that on our website. Go to nexperia.com/support. And it's under the longevity page. We actually list the part, the type, and the package, and we'll guarantee that you can buy that part for 10 years from now. For 15 years, there's usually not an issue with that. I think the best answer is Nexperia will keep building logic devices until you stop buying them. So if you're looking for something special beyond that 10-year posted list, again, contact your sales department, our sales team, and they should be able to work something out for that. That is not an unusual request. And as we've noted, some of our products have been around for 50 years already. We way exceeded the 10 years and the 15 years on those parts already. The next one, do you have a voltage translator buffers with very reduced skew, rise time values less than 750 picoseconds? Javed, Christian, would you like to address that one?
Well, smaller 750 picoseconds we don't have. Rise time values, yeah.
It seems pretty fast, and then the skew
Yes,
would be
very
between
fast.
channels in particular. So, yeah, that would be an interesting question.
Yeah, then we also need some application details in terms of any capacitive loading that it needs to be also able to handle. So.
Yeah, again, we'd love to talk about that one in particular. I agree. I think it'll based on what is your capacitive loading on that device, how fast we could switch the part anyway. But it's something we'd like to look into. And then we cover the next one. And then the very bottom a list here from session 1, how many thermal shock cycles can DQFN sustain without defect of soldering? Christian, I know we did a white paper on packaging several years ago. I don't remember if that one was in there. Do you remember the details of that one?
No, I don't. And we need to get that answer from quality. And I write the answers. I'll put it here on our website.
Yes. Very good. The answer is we do indeed testing of that. I don't remember the numbers off the top of my head, so we will provide that answer in our combined list of questions and answers. Again, if there's a specific issue that the guest who asked that is looking for, please contact us. We do have that information, be happy to get it for you individually based on perhaps your individual circumstances that you're working at. Okay, we still have about 1 minute left, and I see one more question came in. Oh, it's actually advice from one of our own application engineers who are already jumping into it. It's recommended to use high reliability solder for mitigation of effects due to thermal balance. So it is outside of the package itself too. And again, we'll get you that information again. that information exists. It's putting it together to determine the best way to avoid a thermal or a vibration shock for our devices. And I think that takes us to the bottom of our questions. We are now right at the top of the hour, our scheduled top time. If there's no other questions then, what I'd like to do is thank everybody, for our presenters today, for your participation in this event, and for all of our guests who have participated as well too, both from session 1 and from session 2. Again, all the information regarding the questions, the posted answers, how to get recorded versions or copies of all these materials will be sent to you if you've registered. So again, we thank you for your time and have a good day.